In this lesson, we'll be studying the neutralisation reaction, focusing on the chemistry of alkalis. Remember that an alkali is not exactly the same thing as a base. All alkalis are bases, but not all bases are alkalis. A base in aqueous solution is slippery to the touch, has a bitter taste, has a pH of above 7, and reacts with acids to form salts. An alkali has all of these qualities and some other more specific ones. It is an ionic compound dissolved in aqueous solution. It is always made using the positively charged cations of either an alkali metal from group 1 of the periodic table or an alkali earth metal from group 2. For the examples we're going to look at, the negatively charged anion will always be hydroxide, OH-. Some authors have a simpler and more general definition that an alkali is simply a base which dissolves in water. Imagine a beaker containing water and some sodium hydroxide. Now when a base dissolves in water, its cations and anions dissociate, that is, they're free to move about in the solution. The concentration of hydroxide ions in the solution is one way of telling how basic that solution is. So the higher the concentration of OH-, the higher the pH. Now imagine a second beaker, this one containing some hydrochloric acid. You might know from previous lessons that when a strong acid dissolves in water, its H+ cation and negative anion dissociate in a very similar way. So if we slowly add the acid to the alkali, all we're doing is creating an environment where the positive H+ ions can get together with the negative OH- ions and create neutral water molecules. As this happens, the number of free OH- ions in the first beaker decreases, and so too will its pH until it hits 7 and the solution is neutral, although there will still be tiny amounts of H+ and OH- ions present in equilibrium. So here's the equation in full. If we were to continue adding acid past the neutralisation point, there will be an excess of H+ ions and, you guessed it, the pH would drop below 7. So what are the uses of doing this? When we have solutions of chemicals in the lab, it's often really important to know their molarity as precisely as possible. So say we had some old sodium hydroxide solution that we knew was about 0.2 molar. We could get a much more precise figure than this by titrating it with some hydrochloric acid that we do already know the precise molarity of. Here's a video all about titration if you've not heard of that term before. All we need is a way of accurately monitoring the pH and a very handy little equation. Now what this means is that at the point of neutralisation, the molarity of the acid times by the volume used equals the molarity of the base times its volume. If we know 3 out of the 4 terms, we can work out the 4th by some simple rearrangement. So here's your challenge. You've measured out 20.00 cubic centimetres of our mystery sodium hydroxide into a beaker. That's Vb. Our hydrochloric acid was 0.1937 molar. That's Ma. And to make our solution completely neutral required a titration of 22.26 cubic centimetres of the acid. That's Va. Can you work out Nb? Pause the video and have a go. Here's how you rearrange the equation to find Nb. And now we just pop all our values in. So the precise molarity of our sodium hydroxide is revealed to be 0.2156 molar. How did you do? There are other times when neutralising a base can prove very useful. For example, factories that produce clothes dyes create a very strongly alkaline aqueous waste with a pH of between 10 and 12. By law, they aren't allowed to release this into local rivers, but if they neutralise their wastewater, it becomes much less harmful to the environment and they won't get into any legal trouble.